Everyone, welcome to my talk today. Today I'll show you an introduction to Kunlun Distributed DBMS. In this talk I'll call it Kunlun for short. I'll focus on its functionality. First, a brief introduction about myself. In most of my career I worked in Oracle and Tencent. In Oracle I worked on PostgreSQL storage engine and MySQL database. In Tencent I worked on TD-SQL. TD-SQL is the most popular distributed DBMS inside Tencent and on its public and private cloud service. In Tencent, I took the initiative to evolve TD-SQL from a table sharding solution to a distributed DBMS. In August 2019, I left Tencent and started the Kunlun project. The goal of Kunlun project is to build a distributed DBMS from day one with knowledge and lessons learned from TD-SQL. Kunlun should be highly scalable, highly available, fault-tolerant, and crash-safe. It should have premium performance, ease of use and administration, and autonomously. It should be cloud-native and be able to run as a database service. So far, I have finished over 60% of the kernel development. This is our agenda today. First, let's see why we need a distributed DBMS, and then we will see the architecture, basics and examples, and in-depth technologies about Kunlun, and finally the project progress and plans. So why we need a distributed DBMS? First, we have ever-growing data management needs. At the same time, in today's data centers, most data centers use commodity hardware infrastructure. Existing data management solutions have a series of drawbacks and disadvantages, which are causing a lot of pains to application developers and DBAs. First, all these new technologies, 5G, IoT, sensors, robots and drones, autopilot, and so on, are producing a lot of data non-stop. So in the future, we will have a lot more data to store and utilize than today. And most of the data is expected to be relational data. In today's data centers, the hardware infrastructure for computing are mainly commodity hardware. They have moderate reliability and limited computing resources and capacity, and they are deployed massively in multiple data centers and interconnected via network. This makes them very vulnerable and error-prone. Several nodes could stop working randomly and unpredictably for various reasons. And network issues can also produce network partition or congestion issues. And hardware resource bottlenecks can be easily reached. All these issues means some needs for infrastructure software, mainly DBMS. So DBMS should be highly available, crash-safe, and fault-tolerant. And they should scale out effectively and avoid any kind of single-point hotspot or single point of failure. The users of DBMS have specific needs and requirements too. For DBAs and DevOps, they want least human intervention, especially in the case of random incidents. They want DBMS to work autonomously and be able to help them diagnose, analyze, and monitor performance and other issues. Application developers want DBMS to isolate data management complexity from applications so that they can write data access code simply like shown in this picture. They simply execute transactions and queries and handle database exceptions. And they can focus on business logic design and implementation, and their development work can be agile and predictable with affordable cost. So all these virtues require that DBMS to take over all the data management work, and their application can be based on simple logical data layer abstraction. So future DBMS requirements, distributed DBMS should be able to manage terabytes to petabytes of frequently accessed data, with no single point of failure or single point of hotspot. And such distributed DBMS must have multiple read and write nodes, and they should run on many commodity hardwares collaborating effectively, and be able to scale out elastically on demand and run as a database service on public cloud or multiple public clouds. And they should work autonomously and require least human intervention. Next, let's see some existing solutions. First is the common component, the DBMS HA cluster. They generally achieve HA by replicating entire datasets. Typically, there's one primary node for write traffic, so it's unscalable for writes, and there are multiple replicas which can serve read requests. Primary node propagate changes to replicas in the form of binlogs or warlogs. The example is MySQL async, semisync, or group sync for group replication, and PostgreSQL replication. An alternative is replicate data and log file blocks using shared storage. The example is Aurora and its variants. The challenge for a high availability cluster is scalability, because such a cluster does not scale for writes, and that's a big issue if your dataset exceeds the capability of one high availability cluster. That means you have to implement data management solutions outside DBMS. And in industry today, there are 3 typical kinds of solutions to do so. And they all have a series of drawbacks and disadvantages. Let's see the first one. DBMS HA cluster plus middleware, proxy, or gateway instances. Such solutions support sharding and multiple write and read nodes, so they have good scalability, but they often don't support global transaction and query processing. That means in any transaction, you can only write to one shard, and in any select statement, you can only read from tablets of one shard. That means application developers need to often write their SQL queries and transactions according to data physical layout, because they have to carefully write transactions to one single shard, or write select statement to read from one shard. This is not very good. And another solution is to use multiple DBMS HA clusters plus application level sharding implemented specifically in application. That means you have to implement table sharding for each table in your application, and you have to implement cross-shard DML queries for each query, and also global transaction commit and recovery for each transaction. This means a lot of development work in application that should have been done in DBMS. A third typical solution is to use multiple DBMS HA clusters plus microservices. In such solutions, an application is divided into multiple microservices, collaborating asynchronously and loosely coupled via message queues. By doing so, user data is partitioned by microservices. Each service has its own part of data. But the problem is that in application, developers have to handle inconsistency and eventual consistency between cooperating services. And they have to handle service crash safety. Also, there will be more infrastructure facilities. For example, there are a lot of message queue deployments, and also a lot more database cluster deployments. That means more hardware costs, and especially more maintenance and administration work for DBAs and DevOps. Also, the scale out is a problem, because you can add more computing resources for services, but you cannot easily divide services, because services are defined by business domain, not data. You can't just split services endlessly because its dataset is too big for one database HA cluster to handle. And also, some services may still face huge amount of data. So the conclusion is that microservice architecture cannot meet or resolve the needs for a distributed DBMS. In all, the pain points for application to solve data management requirement is that for application developers, they have to write SQL queries and transactions according to data physical location and implement cross-shard transaction. And they will be overwhelmed by redundant and error-prone data management work. For DBAs and DevOps, they have to scale out database clusters manually or handle database node failures manually. They often also have to reconfigure proxy nodes in case of primary switch or when you add or drop a table. That's a lot of unforeseeable chores and routines to do, anytime in any day, so quite error-prone. For business owners, all such solutions mean high human costs and hardware and infrastructure costs, and an unpredictable development time span quality, and a slow response to business changes. Ultimately, there's service or revenue or user loss during database node failures. So we believe the best approach to handle massive amount of data is to use distributed DBMS. Users can manage huge amount of data using distributed DBMS so as to keep application independent from data management work. For architects, this means they can design application with one integral and consistent data snapshot which scales on demand. For application developers, they can focus on business logic implementation based on reliable database functionality. All parts of the application or services work with simple application data. Such data is always consistent and always available, always crash-safe and fault-tolerant and resilient, and always has sufficient resources. So application developers don't have to worry about anything regarding the database management service. For DBAs, they can work more efficiently and productively because the DBMS automates almost everything. So they only leave minimal manual maintenance work for DBAs to handle. And DBAs can focus on valuable work such as data schema design, performance tuning, resource planning, and so on. And the Kunlun Distributed DBMS fully meets all such needs. So let's see Kunlun next. First, the Kunlun architecture. The components in the two boxes are Kunlun components. First, we have computing nodes. They are responsible to accept user connections and also accept user requests and then execute them with all the storage shards and then reply back to the clients. Computing nodes interact with storage shards and also metadata cluster. Storage shards are used to store user data in a share nothing paradigm. So each storage shard stores a subset of user data, and two storage shards have no intersect data. In each storage shard, we have MySQL group replication to replicate changes from its primary node to the replicas. And we also have metadata cluster. A metadata cluster stores metadata about one or more Kunlun database clusters. We also have finally a cluster manager component. It is a program to manage the online status of all the database nodes that are running and that are registered in the metadata shard. Let's see the details. First, computing nodes. They accept and validate user connections and also accept and process user queries. User queries will be received and passed and optimized and executed. The way to execute them is to send certain SQL queries to storage shards and receive results from them, and then assemble those partial results to form the final result and reply to clients. Computing nodes can execute both DDLs and DBMS. In a Kunlun cluster, there can be one or more computing nodes. Each computing node is independent from others. Computing nodes don't store user data. They only store users' metadata locally. That means these nodes take trivial storage space. All user data are stored in storage shards. In Kunlun cluster, computing node is based on Postgres. They support Postgres client protocol and the common Postgres DDL and most of the Postgres DML grammar. In future, we will also support MySQL client protocol and the common MySQL private DML grammars. Next, storage shards. First, we use MySQL replication single primary mode for shard level high availability. So such a shard can elect primary node when a primary node is gone, and it has robust consistency guarantees. In Kunlun, we require Kunlun Percona MySQL. It is developed based on Percona MySQL and contains critical bug fixes and supporting features. And it will advance versions with upstream. Storage shards store application data in standalone tables. That means if you create a single table in computing node, there will be one corresponding table created in a storage shard. If you create a partitioned table, each of the table partition corresponds to one table in a storage shard. Storage shards execute mostly single table queries in a global transactions local transaction branch. Next, the metadata cluster. It also uses Kunlun Percona MySQL. And there can be multiple Kunlun distributed clusters registered in a metadata cluster. Finally, we have cluster manager. It's used to maintain MGR cluster and node online status because database nodes come and go for various reasons. As we just said, hardware issues or hardware faults, power outage, software faults, and so on, or planned maintenance. Anyway, a database node can disappear for any reason, anytime, and we should be prepared for that. A cluster manager also is used to start up entire MGR cluster because the entire MGR cluster could exit at the same time. So cluster manager is responsible is used to start up it in that case because such a cluster cannot start up by themselves and connect to each other automatically. One cluster manager can work on all Kunlun clusters registered in a metadata cluster. Let's see some examples. First, these are some metadata tables stored in the metadata cluster. We can see all the computing nodes and the storage shard nodes are all registered here. Next, These are metadata tables stored in each computing node. With such information, a computing node can connect to its storage shards and metadata cluster nodes. Next, let's do some DDLs. First, we create a database called ecom and then connect to the database and create a partitioned table called orders and all its 4 partitions. We can see from the PG class query that there's an additional new column called real shard ID. In each such field, the number shows where is the tablet stored, in which shard it's stored, so that with such information, computing node can know where the table is and connect to the storage shard to read or write the tablet. Then we connect to another computing node of the same Kunlun cluster. See, the port is 6402. The first one is 6401. So in 6402, we can also access the tables we just created, and the metadata is exactly the same. Finally, let's see the metadata in storage shards. In the 2 storage shards, we can see the database called ecom public is automatically created. They are created when the create database statement was executed. And we have all these 4 tables. Each table corresponds to 1 table partition in computing node. And this is the metadata. So in the Kunlun cluster, this partition table has its 4 partitions well created in the 2 storage shards. Then we do some DML and transactions in computing nodes. First, in the 4 rows, and we can see the rows, and we can see each of them stored in 1 partition. And then do an update statement. It's an auto-commit transaction. And you can see the update takes effects. And then let's see the DML transactions in storage shards. First, there are 4 rows in each, one in each tablet. And you can see in the bin logs in each of the shard, the update auto-commit state transaction is executed as a 2-phase commit global transaction. Local branch. So in this storage shard, you can see this transaction. This is its first phase. This is the second phase. In the second shard, we can see its first phase and the second phase. So the computing node did a 2-phase commit to commit to the auto-commit transaction. Next, let's see some in-depth knowledge about Kunlun database. First, table sharding. We have mentioned this in previous slides. Computing nodes can map tables and table partitions on computing nodes to its correspondence in storage shards. Kunlun's table sharding completely uses Postgres table partitioning feature, so the usage is exactly the same. Users can specify shard keys in create table statements. The shard key can be any group of columns, and the sharding method can be hash, range, or list. The range method is very flexible. You can add more partitions as your business runs. For example, you can add 1 partition for each week, and you can retire old partitions, for example, 2 years ago. The computing node can map rows of table partitions to its target on storage shards automatically. Next, the global transaction coordinator. It does two-phase commit for transactions that write to multiple storage shards, and it does one-phase commit for transactions which writes to one shard or zero shards, and also for the local branches that are read-only. Kunlun's global transaction can resist node failures and network issues during commit. That means if a computing node crashes, or the primary node crashes, or all their connections disconnect during a global transaction commit, the global transaction will be in a consistent state. It will either be totally aborted or it will commit successfully. With this feature, application developers can use transactions as if they are using a standard database. And they can write to multiple storage shards in a transaction. Next, the storage resilience and auto failover. This means a computing node can adapt to primary node failures of storage shards and metadata cluster automatically. They always use the latest primary node to write, and they can check against potential issues of MGR. Let's see some examples. First, we connect to the committing node 6402, and we can see the shard metadata, the master node of each shard. Then we do an update, and we succeed. And then we queue the primary nodes of the two shards in another session, and then we do the update statement again. This time we fail because of this error, because the connection between the committing nodes and the primary nodes broke, so the statement fails. Right now the computing nodes are looking for the new primary nodes. Here the primary node ID is not yet refreshed, and we try the update again and it fails again, and after a few seconds we try it yet again. This time we succeed. You can see we have succeeded, and then we can see the shard metadata, the primary node ID have been updated. This means the two storage shards have elected their new primary node, and this computing node have also figured out the new primary node and updated its metadata. So that's why it can successfully execute the update statement again. All the primary election auto failover completed within 8 seconds. And for the client application, what they see is an error thrown from database. So all they have to do is to try and catch this error and re-execute the transaction again. So they don't have to worry about what the database system is doing. Actually, behind the scene, Kunlun cluster has done a lot to make everything right. Next, let's see the global deadlock detector. Why a global deadlock can happen? It's because local waitfall edges form global cyclic waitfall graph. The local waitfall edge isn't a cycle by itself, so it cannot be detected in a single NDB instance. So global deadlocks can only be detected and resolved in computing nodes. Computing nodes do so periodically, or when a statement waits for its results from storage engine for a little while, and it will ask the computing node background process to do this global deadlock detection. This is an example. First, On shard 1, we have GT1 waiting for GT2's LT1. That means GT1 is waiting for GT2 in shard 1. On shard 2, we have GT2 waiting for GT1, and this forms a cycle. So this is a global deadlock. In the two pictures, we can see in the first transaction on the left, it's updating the row with ID 1. On the right, the GT2 updates the one with ID 3. This happens on shard 1, this on shard 2. And then the GT1 tries to update the row with ID 3, and the GT2 tries to update the one with ID 1. And this global deadlock is formed, then resolved, and this query on storage shard is queued. It returns error, so the global deadlock is resolved. So when we do this rollback, and this update statement will successfully return, and we can commit it. So this is how a global deadlock is formed and resolved by computing nodes. If you write your application to manipulate multiple storage shards, you will have to implement the global deadlock detector too. But you cannot do so without supporting features that so far only exist in Kunlun's Percona MySQL. That means if you are using a official MySQL, whether it's 5.7 or 8.0, you cannot do this global deadlock detection and resolve. The only alternative you have is to use lock timeout. That means you have to wait until one of the statements times out because of the lock timeout. That often takes about like 10 seconds or 20 seconds. You cannot set this variable too small, otherwise normal DML statements may just time out when we don't need to. So this is the value of the global deadlock detector in Kunlun computing nodes. Next, let's see the DDL synchronization. We have seen the example in earlier pages. The key is that this feature doesn't require human intervention, so that DBAs don't have to do anything to make this work correctly. And they are executed in storage shards automatically too, and replicated by all other computing nodes, so that all computing nodes always share the consistent metadata. DDL executed as auto-commit transaction. That means when you execute a DDL in Kunlun, if any node crashes or just falls or stops working or exits for any reason, your auto-commit transaction is in a consistent state. It will either be aborted or committed. The only unfortunate complex is that MySQL 8.0 the atomic DDL isn't revocable. That means under certain circumstances, DBAs have to intervene and do some manual check. And of course, such work can be automated by scripts too. Also, computing nodes can do concurrency control to allow consistent concurrent DDL execution. Next, let's see scalability. First, in the future, it's under development now. We will have replica read feature so that computing nodes can read from replicas of storage shards. Also, currently, a computer node can do async data read and write with target storage shards. That means a query is actually executed parallelly. So that means higher performance. In future, we will also implement the balanced tablet redistribution on new storage shards. That means if you add one or more empty storage shards to an existing Kunlun cluster, some of the tables will be automatically redistributed to those new storage shards elastically, continuously, or on demand, or automatically, all done at background and undetected in application and or by end users. So with this feature, users can use Kunlun cluster in a typical cost-effective way. That is, you can start with one or a few storage shards. And when your business grows, when you have more and more data, you can scale out on demand very easily and simply automatically. Next, let's see Kunlun storage shards. The key to make global transactions crash-safe and fault-tolerant is for MySQL XA processing to keep transactions executed in InnoDB and logged in binlog identical, and also keep transactions executed and logged in a primary and its replicas identical. And in MySQL 8.0, we also need the set of GTIDs ever stored in InnoDB undo log identical to those logged in binlog. However, a series of bugs in MySQL 8.0 cause these guarantees to fail when MySQL server process crashes or exits abnormally, for example when a power outage happens. In Kunlun, we fixed these bugs so that whatever incidents happen to the MySQL server process, these guarantees always hold true. Also, in Kunlun Percona MySQL, we enhanced its performance. At most 50% of QPS increase and 50% latency decrease can be observed in Sysbench read cases. This article has details about this performance improvement. We improved its performance so that there will be less frequent jitter in QPS. Also, we developed many supporting features needed by computing nodes, such as the one needed by global deadlock detector I mentioned earlier. There are some issues in MySQL group replication that should be mitigated, and if you are interested in these details, you can look at this bug. Currently, these functionality have been completed, and recently Kunlun 0.7 was released, and it's POC ready. So you are welcome to do some POC test and so on, and see if Kunlun can work for your solutions. The ongoing development is the 0.8 version. We will focus on query processing and the query supporting features. These are some technical information at these places, and you can download the 0.7 release here. We will build a website for this project and the startup very soon in the future. This is what we will do in the future for 0.9 and higher versions. Basically, we will make the Kunlun project to work on cloud, on multi-clouds, and also the elastic scale-out will be implemented. Also the support for MySQL and more DLLs and so on. This is what I want to say in this talk. Thank you very much for watching. Goodbye.